Welcome back to the lab. Got a very exciting video prep for you guys today. Is going to be an excellent way, absolutely excellent way to end our series on comparators. I have a design example just for you, and basically what we're going to do is we're going to run through some of our calculations for the thermal runaway monitor. Check that series out if you haven't already. Codename Seth, that was a really fun project that we did a while back, and I very much enjoyed it. So what we're going to do is a deep dive into specifically how we designed the latching comparator threshold. It's absolutely excellent. It basically requires a power cycle to reset this comparator circuit. It's meant to be like a critical overvoltage or undervoltage type of circuit. It's a lot of fun, very useful. Let's dive in. Actually, before we do that, one little comment. We want to do some Q&A, some more informal get-to-know-me type of content. So if there's anything that you'd like to ask, make sure to drop that in the comments. We'll be taking a look at our videos and grabbing some great questions out of there. If you're plugged into our Slack channel or Twitter as well, you can send them to us at EE for Everyone or by responding to our post in the Slack channel. Awesome. Thanks, guys. All right, back to where we're going. All right, what do we have? What do we have? Obviously, a ton of fun ahead of us today. What we're going to do is we are going to be talking about comparators one last time. Comparators, they're excellent little pieces of electronics. Just to get you caught up if you haven't been with us a while, there's a positive and a negative, and you get your two inputs. And when this input, let's change colors. When this input is more positive than this input, the output is high. When the other is true, the output is low. So, excellent. That is the basic operating principle of a comparator. If you want to learn more, definitely check out our last two videos. We just did two great videos that walk through ideal and real comparators. Don't miss it. Anyways, we're doing our design example. All right, let's start by laying out our goals for this circuit. All right, goal to first. We want to minimize voltage sources. What I mean by that is there are some, I'm probably gonna, sources, I probably misspelled that. Anyways, we want to minimize the number of voltage sources because you can grab like precision series or shunt voltage references and they do a great job. Like they are very useful, but they're kind of expensive and it's just more parts. It's more opportunities for failure. So we want to keep this pretty simple. That means that we might be giving up some accuracy. We might be giving up some accuracy or maybe some precision, perhaps both, but we don't need it. Not for this. This was coming back to our thermal runaway monitor where we were looking to detect like 50, 100 volt. Like we want to know the difference between normal operation and burning your house down. Like we don't need laser precision. We don't need a super accurate threshold. We just need to know that it will trip within some bounded tolerance range that will be safe. Okay? That's where we're going. So we want to minimize the number of precision. Maybe that's a good precision. Sure, we'll pretend that squiggle says precision. Voltage sources. All right. But that said, we don't need it to be the most accurate thing in the world, but we do want it to be reasonably accurate. And that's reasonable to me, not reasonable to you. These are terrible. These are not requirements. These are not requirements. These are more guidelines. Design intent, whatever you want to call it. It's not requirements. Reasonably accurate. I'm going to put that right in there. To me. Oh, it sure is fun. Anyways, so that's basically what we're trying to do. And it needs to latch. For the sake of this video, for the sake of this example, we're going to say that the critical threshold is 1 volt on whatever we're monitoring. So basically, the comparator should be fine, but once we exceed 1 volt, we want to turn off and stay off forever. All right, that is our design challenge. Okay, so to give you a plot of the expected behavior, we're going to draw a little graph. This is time, this is voltage. So we're going to draw in our 1 volt threshold. All right, how do we expect this to behave? Okay, so we are going to start from t equals 0, and we're gonna, oh, look at this. Woo! It's going everywhere, but then we cross over that threshold. Okay, how do we expect our circuit to respond? Well, in this case, we're going to be using, let's see, should we use a push-pull or an open collector comparator? This is a design choice. We can do this with either type, but our decision will have impacts. A push-pull comparator can either source or sink current. So that means it will either be pulling the output up or pulling it down. With an open collector comparator, that means our only choice is to let go or to clamp the output to ground, which changes the behavior. In this case, I think I'm going to use an open collector comparator for 2 reasons. The first reason is because that's what we used in our other project, so this will be pretty similar. This will kind of look the same as it did then, but also I want to use this because it allows for putting multiple comparators in parallel. So you can have one pull-up resistor on the output, and then if any of your thresholds trip, it'll pull it to ground and you'll know that there's a fault. Why did I need to walk through that? Why did I need to talk through that? Because that was determining which state our error state is. That means that for this design, 0 volts equals fault, and the converse or inverse of that is that greater than 0 volts equals okay. So that means we're going to have our output pulled up to, well, probably 5 volts-ish, somewhere around 5 volts. So we're going to need to have a discount, V out. What do we expect to see then? No fault. We're doing great. Everything's good up until this point. Then we expect to see it say there's a fault, and we expect it to stay there even after the fault condition resolves. This is our intended design. Make sense? This is what we are trying to build. Where do we start? We need to start with the architecture. How is this going to look? We've got our 2 inputs. We've got I'm just going to rough this in. Let's pretend this is a 5 volt LDO. So then we've got a 5 volt 1% rail. So that means it's a 1% tolerance around 5 volts. Sweet. And we're going to use that to power a comparator. We're going to name this node. We're going to call it not error. This is our output. And then we're going to supply 5 volts. We're going to need to add a pull-up resistor. And now we need to think about this. We need to think about which terminal of the comparator should be connected to what. Now remember, we want this to function such that when the pink line, when V in exceeds our threshold, we want the output to go negative. When this is more positive than that, we want it to go negative, which means that this would need to be our negative input. If this is our positive input, the flat 1 volt line, if our reference is the positive input and the pink line, our signal input, is the negative input, when the negative input becomes more positive than the positive input, the output will be pulled to ground. That is the intended function. So, in our design then, we're going to draw our input. We're going to call this sig. Nope. We're going to call this in. And we're going to call this ref. Okay, so we have a few critical nodes, but now you might notice this looks exactly the same as all of our other comparator problems. So where's the latching? Well, here's where the latching comes in. We need to add something else, and it's going to be tied back to this output. Now, there's a couple things that we could do. We could put a diode here and a resistor, or even just a diode. But we know that this is an open collector comparator. So you might notice there's some simplification that can be done, because here's a resistor that's pulled up to 5 volts and connected to this node. Here's a resistor that's connected to that ref pin. So we could, in theory, just get rid of that resistor, get rid of that diode, and then this becomes our voltage divider, where the reference would literally go from the threshold to 0. Like, that would be an incredible amount of hysteresis. It would become literally impossible to change states back the other way. 0.7 volts is pretty low, but I guess compared to a volt, I would be using a Schottky. We'd be using a Schottky. So we'd get a lower bias. I'm pretty sure we did pretty sure we've done an episode on types of diodes. Check that video out. Check that video out if you haven't seen it. Okay. So what do we want to do, right? We're faced with another design decision. Now remember, one of my goals, I don't even think I wrote it down here, but I want to be able to use multiple of these in parallel. So that becomes more difficult if we use this resistor for 2 functions, because then if we had a second comparator, that gets a little messy. So that means that in some ways, this diode would help us out quite a lot. Though we've got more choices than that, right? What we really want to do is clamp, what is going on? There we go. What we really want to do is clamp this node to ground. So in theory, we could use a FET, or we could use a BJT. We could use all kinds of technology, all kinds of devices. Well, how do we choose the right path? It's hard to say, but here's what I think we should do. I think let's take this the simple way. Don't make it more complicated than it needs to be. A simple diode, and we're going to be targeting something with a very low forward voltage. Much less than 1 volt. If we can find something in the 0.1 to something range, that would be pretty good. Okay, so that becomes an implementation detail. Something that we can do to help us in that regard is by having a very low forward current, because as forward current climbing the IV curve of a diode, the higher the current, the more voltage will be dropped. So if we make this pull-up resistor relatively large, that might help. But if we're going to make that resistor relatively large, let's say we're at 5 volts, 1 kilo ohm would be 5 milliamps, let's say 10 kilo ohms. If we make that a relatively high impedance, now we might have some issues with noise here. There might be some opportunity for noise to couple into the system. So how can we accommodate that? Well, we could put a little capacitor pretty close, maybe a 0.01 mic, something like that. That could be an implementation detail that would help us out. Okay. So now it looks like we have a voltage divider, a simple voltage divider. I'm going to make these comments in another color. I'm just going to start pointing out what we have here. We have a 5 to 1 volt voltage divider that we need to make. We need to figure out what kind of diode we're going to use there, and then what our hysteresis would be. Because if our reference voltage doesn't actually drop all the way down to 0 volts, that means there is a voltage on the negative input that could, in theory, reset the circuit. That's not our design intent, but as long as it's a sufficiently small voltage, that might be okay. And then we need to make a design decision out here as well. We need to pick a resistor value. I think in this case, let's go for a 10 kilo ohm as well. It's not a super critical value, but I think that adding a little capacitor out here would be a good idea as well. Okay, now there's only one more thing that we need to think about before we dive in and perhaps even start to simulate this. And that is the thought of startup. This is a latching circuit. If we power on instantaneously and everything just goes to its steady state value, we'll be fine. But that's not how life works. We're going to start where everything is 0 volts and it all needs to ramp up and it needs to do something. And will this circuit be able to actually ride through that power on, like transient, latch into the untripped state and then later trip? If this is a critical overvoltage that shuts down your system, that's pretty important, because if the circuit doesn't work, your system won't power on ever, because every time it powers on, it'll trip this circuit. That could be a huge deal. Okay, enough rambling. As long as this input voltage is less than our reference, we'll be okay. So what we want to make sure is that reference gets a little boost on the power on. And how I managed that in the past is by putting a capacitor, this is going to be kind of hard to draw, in parallel with that upper resistor, something like a 1 mic. That'll just give us a little boost of current, and we need to get into AC circuits so you might understand why, but basically that capacitor will ride up with the 5 volt rail. It'll go kapoing, and it'll drag that reference node up to about 5 volts, because there's 0 volts across the cap. If you pick up one side, it'll try to pick up the other. Then that capacitor will slowly discharge back through the 10K over time, but in that turn-on moment, when the input is 0 volts, it'll just make sure that we ride through that transient. Yeah. That's especially important in this case because we've got this latch circuit, and in fact, that diode could be a huge problem for us. So let's add a provisional component here, really small, like 100 ohm. So We're 2 orders of magnitude less than our 10K. But that's there just to limit. So if the output does have a glitch and we try to pull our reference down as a startup glitch, that 100 ohm will limit the peak current and make sure that the reference node can hold itself up for long enough that we'll be okay. That might have been a little hard to follow. You'll see that in the simulation later. Okay, so really simple. All we have to do is 1 voltage divider. Let's get that set up. So V out equals V in times R bot divided by R bot plus R top. Excellent. In this case, the top is 10K. The bottom is question mark. We're going to call that RB equals, great. Okay. V out is 1 volt. V in is 5 volts. This ends up being RB over RB plus 10K, because that's a 10K resistor. Multiplying both sides by this quantity down on the bottom, we end up getting 1 volt. All right. Yeah, we end up with 1 volt times RB plus 1 volt times 10K equals 5 volts times RB. Now, yeah, we just need to get the RBs together. So we end up with 1 volt 10K equals 4 volts RB. And I'm not going to worry about orderable part numbers here. We're just going to hope this all works out. Excellent. So we're going to divide both sides by 4 volts. Okay, this unit cancels, and we end up with 10 over 4 kilo ohms equals RB. 2.5. Oh my goodness, that should have been way easier. There we go. Simple. Easy. All right, so we're going to try to switch gears. I'm going to capture this in LT Spice, install a live annotation tool, and we'll see what we can do. Back in a flash. All right. We've got some sweetness captured in our favorite circuit simulation tool, LT Spice. And let's just walk through. There we go. Let's just walk through some of what we got going on. So we've got our 5 volt source. We have the feedback / hysteresis network thing going on. We have a very messy voltage input source. That source is really just there to figure it out. The only thing that's kind of weird about this whole setup, if I'm being honest, is this right there. Because LT Spice doesn't have a whole lot of truly open collector comparators. So this is kind of like an open collector comparator. It's an open collector comparator with a built-in current source. So we have a current source in parallel with our 10K resistor, but that's okay. It'll still work for our demonstration. It's just not quite exactly what I had in mind, and that is okay. So in order to really show you what's going on, let's run the simulation. And this gives you an idea of what we have as V in. It's this really, really messy, kind of swaying all over the place type of signal. And there's our reference. You can see that it's pretty much spot on, 1 volt. So that's good. Our voltage divider worked, which it should. Is a pretty simple voltage divider. I'd hope we could do that correctly. But you'll notice this isn't ideal. This isn't quite what we had imagined. That's a shame. It's not quite what we were hoping to accomplish. Yeah, that's not great. That's not great. And why is that? Well, let's take a look at our reference input. Hopefully that's a little easier to see. I just made the waveforms a little thicker. So if we look at this reference and we look at our input, you can see there is a great deal of hysteresis, but not quite enough to keep us latched forever. In fact, we actually go negative, which means, okay, ignore that. Ignore that negative voltage we're applying. I don't like that at all. Perhaps what somebody should do is grab a diode and perhaps clamp that to ground so that we don't do that anymore, so that things work. Okay. Hey, look, we don't go negative a whole bunch anymore. So you can see what we're doing is we're just clipping off that negative part of the waveform. Yeah, whatever. We're good. We're fine. Everything's fine. Okay, the point that I was trying to make. This is not close enough to 0, right? We are able to retrip this comparator. For some applications, I think actually for our application, this was close enough because our threshold was closer to 2.5 volts, and when you go from 2.5 to 0.2 or 0.3, that is quite a lot. An order of magnitude on your threshold for hysteresis is pretty excessive. That is pretty excessive. Let's just for a moment, let's brainstorm how we might be able to make this a little better. What we really want to do, like the pinnacle of what we would like to do, is basically cut this trace whenever the error trips. That would be like perfect. There's a couple ways that we could do that, but that seems like it's a little off the beaten path. That seems like it's a little out of scope of what we're trying to do today. So perhaps what would be more relevant would be if we, for a moment, just pretend that our threshold was actually a little higher. I'm not going to recalculate the voltage divider. I'm just going to move our threshold around. Let's run that. Let's see how we do. So our reference is now right around 1.7 volts. Oh, you gotta be kidding me. I just can't win with this thing. I just can't win. I keep pushing it too close to negative. Okay. So now, even though our signal crosses below that threshold pretty substantially, it remains tripped. My goodness, that was more difficult than I expected. Okay. So there's a couple elements from this circuit that are not being modeled. You might remember that 1 microfarad capacitor that we wanted to put across in parallel with that 10K resistor. I intentionally omitted that so that I could show you what that looks like in real time. By adding that capacitor to the ref node, what we're going to see is we're going to see a little bit of a transient right here. We're going to see something that looks a little bit like this. That's what I would expect. And then it'll kind of round off these corners just a little bit. That's what I would expect. Rerunning the simulation. And hey, look at that. There's that little transient. And okay, I might have made it look a lot more dramatic than it really is, but there's a little bit more rounding on those corners. Excellent. But overall, right, the steady state threshold wasn't changed, and the overall circuit function is working. That's pretty cool. We have a latching comparator circuit. Yes. Interestingly enough, it looks like there's a little bit of an input offset voltage. You can see the difference between the trace, and ideally this would be 0. There would be no voltage difference here. But because of the way this thing is modeled, it being the comparator, you can see that it's exhibiting some of those non-ideal characteristics. If we look at the input current, you can see that it's not 0. It's quite small, but it's actually, that bias current is sometimes positive, sometimes negative. This is actually behaving quite similarly to how we described in our ideal and real comparator walkthroughs. What a surprise. Oh, I'm glad that we're not totally insane. Yeah, so that's pretty much all I wanted to walk through. That is, yeah, that's kind of the thing. That's the punchline. That's the capstone. That's all I got on comparators. No, I'm just kidding. Hopefully you enjoyed this walkthrough. Hopefully you had some fun walking through this design example with us. I know that I had a lot of fun walking through this with you and trying out a new tool. Thanks again for reaching out and showing us that live annotation tool for Windows. That is fantastic. Makes it way easier when I can draw an arrow and show you what's going on. Honestly, I wish that I had more to say about this design example because I think it's very interesting. I think this is super cool, but unfortunately, it's pretty simple. And we've been walking through comparators for quite a few videos, so I think we're going to have to leave this one here. Never fear, we have a lot more great content on the way. We're going to be kicking off a new series that I am calling What Even Is. That is the new series. It's going to be kind of similar to the comparator, but a little bit less focused. And this is going to be walking through the design of a current source. We're going to start from what even are current sources, which is going to be a very high-level conceptual walkthrough of the difference between a current source and a voltage source, which will finally give us an opportunity to walk through a mesh analysis where we can plug in numbers and solve it right. There's so many voltage sources in the world. It makes nodal analysis so much more convenient. Anyways, and then we're going to build a BJT current source, build one out of an op-amp, improve its transient response. It is going to be fun. We've got a lot of great content planned regarding current sources. If you like this video and you can't wait for more, let me know by getting subscribed, hitting that like button, and leaving a comment down below. If you want to support the channel, consider checking out our Patreon page linked in the description. It really helps us out a lot. Thank you. Also down there, you'll find some links to these design tools that we're using, the annotation tool, and that simulation. If you want to crack it open and adjust our hysteresis to make it even more aggressive. It's awesome. Thank you so much for those of you that make this possible. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching Eat You for Everyone, and thanks for staying till the end. Bye!